Yeah, so welcome back. In today's lecture, we'll talk about software quality management and the models. So, normally on a regular day, it would have been a holiday on the occasion of Mahavir Jayanti, I guess. And since we are going through this online mode, so I thought in order to keep a smooth track of this course, and in order to finish this course in time, we should be in touch with all these topics on a frequent basis. So today we'll talk about unit 4. We'll be starting our unit 4, which talks about software quality management and models. So in this unit we will talk about modeling processes. We'll look into some of the software reliability models. We'll talk about your Rayleigh model, the Putnam model we use, a very much familiar term, the Putnam model, and a broadly used term as well. Plus, in the next lectures, in the coming lectures or the videos in this scenario, we'll talk about exponential distribution and software reliability growth models. We'll also talk about software reliability allocation models. We'll see the criteria for evaluating all these models, which we'll go through. We'll talk about 2-3 models today only. We'll talk about some categories, some subcategories of the models. Then at the end of this unit, we'll talk about the software quality assessment model, which is like your hierarchical model, which is used for the software quality assessment. When we talk about software quality assessment, it's like measuring and then taking some managerial level decision in order to enhance the quality, because once we have measured, we have identified where we stand, and based on that we take some calls in order to enhance the quality of the product and enhance the overall quality of the development process as well. That means all these steps which are included in this software development life cycle, for every step I need to bring some improvement. As we say, right, there is always a scope of betterment, right? There is always a scope of improvement. Here also, my ultimate aim is to analyze it with the help of some models which we are going to study, and then ultimately improve it, ultimately assess it. Now, to start with, what we have is we have some models, right? So these models are broadly used, and the primary purpose of this measurement and analysis activities are to provide some feedback, right? Some feedback in the form of some useful information in order to manage the software quality. Plus, as I said, all these steps involved in software development lifecycle processes. So the quality of engineering process is also managed and analyzed. Plus the overall software development or the maintenance process and the underlying activities involved in this entire phase. The feedback and the information provided basically are based on the analysis results. These analysis results we get using various models, and the data collected for the sake of quality assurance, and this data is collected from all the general development activities plus the processes and procedures we are following. So in this unit, what we'll do is we'll examine and we'll classify, we'll state, we'll study some of these models, and then we'll be comparing some models. We'll come up with some strategy in order to select these models. So from the initial discussion, you might have got some idea that these models are basically for quality assessment. And when we say quality assessment, so once again we are talking about your SQA, which is your software quality assessment part. So And these models which are going to study are the analytical model. So that would provide you some quantitative assessment of the characteristics, or maybe sometimes the sub characteristics based on the measurement data from these software projects we use. And these models basically help us obtain an objective assessment of our current product quality. Just because what we do is, in these models we obtain some of these quality assessment. That means we are talking about the current quality product, in contrast to the often unreliable subjective assessment based on the personal judgment or the imprecise quality assessment. See, many times what we say is based on the subjective assessment which is done on the basis of personal judgment. For me, let's say agile development might not be accurate, but for someone else, for a specific product, he or she may feel that this particular thing is something which is a very quality process, right? Or any of the specific step which we are using in order to come up with a particular product. So most of these things are something which are quality, subjective in nature. And for looking into the attributes which are subjective in nature, the best thing is we need to come up with a feedback kind of strategy, or we need to come up with some matrix, and then we can assess it and then we can manage it. And these models, the models which we are going to study in next few slides, can provide us with an accurate prediction of the future quality, and this can be used to help us make your project schedulings, or maybe the resource allocation and some other management level decisions we can take. So recall in our previous discussions, in one of the models we were talking about predicting the performance or one of the non-functional attribute of a to be built application based on the data which we had from the previous existing applications. We, in one of the discussions, we said that let's say for a particular company is coming up with, let's say, 15-20 projects. So what we can do is we can use this data from 15-20 projects and analyze it, and then we can predict some of the quality attributes of to be developed application, or the application for which the development is ongoing. So then we can definitely look into the project scheduling part, plus the resource allocation, plus the budgeting, plus overall management decisions level. See, it's like these days what you see is that everyday government is taking some measures. It can be in the form of imposing section 144, it can be in a form of imposing a strict lockdown. That too based on the kind of data which they are receiving continuously, they take a call that okay, let's declare this particular area, XYZ area, as a red zone because the number of cases are rising. So in order to spread this, in order to avoid spreading this disease, let's take some strict action. So something like at the management level, we take some decisions based on the data which we are getting. Plus there also you see a lot amount of research paper coming claiming this, if this is the figure, this is going to be the condition, this is to be done in order to reduce the number of cases and so on and so forth. So all kind of models are working at a back end in order to come up with some decisions which the government or maybe the administration takes on daily basis. So there also we need to have some models. Here also we need to have some models for some sort of assessment, and in our case we are talking about software applications. So the ultimate aim is the quality assessment, which as we said that in every phase of software development life cycle we need to look into the quality aspect. Now In addition to this, some of the models can also help us to identify the problematic areas. Ultimately, it can help us in taking some appropriate remedial actions which can be applied for the quality and process improvement. Right. So from these models, we can get to know where the lacuna is and where the problem arises. So maybe from these models, we let's say we apply any particular model, and then we get to know that okay, in the testing phase we see good amount of failure, good amount of issues. So I need to bring some changes in the testing team, or maybe I need to let my test engineers undergo some of the testing training of the testing tools, or maybe some other managerial level decisions in order to take care of this particular issue. So ultimately it is leading to the overall quality and plus the process improvement as well. That means from, let's say, we are applying a particular heuristic approach in order to test a particular product, and then we analyze that okay, this particular technique is not helping us in identifying or uncovering the defects which are there in my application. So in that case, what we can do is we can improve the process. That means we can come up with another heuristic approach, and which may be able to uncover some more defects which are there in the particular project. That means the success rate of this particular heuristic approach might be relatively high. So it would be like we were applying a technique X, now we are applying a technique X prime. Both these things are heuristic approaches, and this particular X prime is yielding a better result. So it is something which is the overall process improvement, because we have improvised and we have improved our process, and we are able to come up with a quality application plus an improved version of our process in which we were involved. Now, so these models are broadly classified into your generalized quality evaluation model, or the product specific quality evaluation model. So from the first one we get to know an idea that okay, this is something which is a generalized one, and in the next one we have a product specific quality evaluation model where specifically for a particular product we are coming up with a model. And then this further we have some sub classification as well. So we'll see these things in the upcoming slides. So as far as your generalized quality evaluation model is concerned, it has further three categories. One is your overall model, next one is your segmented model, and the last one is your dynamic model. In case of your product specific quality evaluation model, we have something called as a semi customized model, and then we have like observation based model, we have measurement driven predictive model. So in both the cases, in case of generalized, we have some three categories. We have in case of your product specific quality models, we have further three categories of the same. So to start with, what we have is we have your generalized quality evaluation model where we have like overall, segmented and dynamic. Let's see what these three things are. Overall, as the term suggests, it is much more generalized, and of course we are talking about a generalized quality evaluation model only. So what we have is we have like product specific model where we have like semi customized, we have like observation based, we have measurement driven predictive models. In today's class we'll try to, in this class means this particular video, we'll try to finish at least three, I guess we'll be able to finish these three particular models. So to start with, what we have is we have something called as your generalized quality evaluation model. In this we have three categories. So we have like overall model, which provides a single estimate of overall product quality. So it's like very generic, very shallow kind of approach. In case of segmented model, we'll see, don't worry, we'll see all these models in detail in the coming slides. So in case of your segmented model, this provides you with different quality estimates for different industrial segments. So it's like for all the segment of the application, I'll provide you a different quality estimate. Whereas in case of your overall model, it is like single estimate of overall product quality. And your last one is your dynamic model, which provides you a quality trend or distribution. So you'll get a kind of graph of distribution graph or the quality trend. Or it can be over a period of time, or it can be over a development phase, like for every phase what kind of quality we have or the issues which we have, that we'll see in case of your dynamic model. So to start with, we have like overall quality model. So this is something which is like very general, very subtype, general subtype, generalized quality model. And as we said that it is giving you a single estimate of overall product quality. So it is giving you a very rough estimate of product quality without requiring any product specific measurement or like even a general characterization of the product segment. So it's like it gives you a quality attribute, and it gives you a measure of let's say Facebook app, let's say for example. So it is not giving you like whether it is for a handheld device, Facebook app, or a web app or something else. So it would be like overall quality. So a very generic one. And then just because of this nature, this model is providing you a very rough estimate of the product quality. As I said, see, web application has a lot more different features, characteristics, and the platform on which it is running as compared to your iOS or Android. So in that case, it is providing you different kind of figures. Now, next is this is one of the example of your overall model, where your defect density can be defined as the total defects upon the product size. So in this case, the product size is often measured by the lines of code or maybe function points. So it is like given by Can in 2002, a very popular article on this particular thing. So basically this model would lump all the products together, and it is going to provide you a single defect density estimate based on all the observed defects for all the products. So irrespective of what kind of product it is, let's dump all the data, come up with an analysis. So of course you are going to get very rough estimate. So various product sizing models can be used in conjunction with defect density in order to estimate the total defect for a given product. So the overall model can also be an abstraction of the commonly observed facts about the quality, which is like generally true for all kind of application domains or the product segments. See, as I said, I'm considering everything for Facebook, like all the platforms and everything, where I know, whereas I know the product and the characteristics are totally different in case of a web application plus an application for a handheld devices in the form of your iOS or for the Android platforms, right? Both the things are very different. So what we have is that this particular model comes out to be a faulty one, you can say. Not faulty, but yeah, with coming up with a very rough estimate. So as a title suggests, overall model, so it is something which is not the accurate one. Yeah, so in the next one what we have is like we have the segmented model. So in this case we have some general information about the product, and this product is which is under the study, and we have some general information available to us. So we can use this segmented model instead of your traditional overall model in order to get some better quality estimate, right? So in this case it's like something which is very vague. So here it can be like I can take the defect density model, which can further be refined, right? Defect density we saw in the previous case, right, in the overall model. So it can further be refined into a segmented model if we use like market segmentation to group products and provide different defect density estimate accordingly, right? So like we can also have like sizing models tailored for different product segment, which can be used with such defect density models in order to estimate the total defect of a given product. So some amount of improvement we are getting as compared to your overall model, some amount of improvement, and resulting into this particular segmented model. So segmented, from the title itself we are getting an idea that this is something which is talking about a specific segment. So we have categorized and then we are coming up with some data, so that will at least be somewhat better than your overall model. Now this is one example of a segmented model for the reliability level estimation. Let's say we have like for a product which has like the categories are like safety critical software, and then commercial software, and then auxiliary software. So three categories we have. Then we have like failure rate under this, and then we have like reliability level, and which can be your ultra high, high, moderate, or low. So this gives you an example of a segmented model based on some amount of empirical data which estimates the reliability level for the different product segment. Three particular product segments we have. Like, see, product segment can be any. I can add another segment which talks about financially critical application, right? So I can add another one. So here what we have is we have like three product segment. So basically this data, this particular table I took from Leveson, which gave this idea 1995. So here what we have is like three major product segment. One is your safety critical software, such as your control software for medical devices or maybe for nuclear reactors. In case of your commercial softwares, we can have like telecommunication softwares or maybe any business applications. And in case of your auxiliary software, we can have like computer games and some, you know, tally kind of applications, some low cost PC softwares. So here the reliability level is measured by your failure rate, or maybe the average number of failures per operating hour, right? So number of failures per operating hour. Now the next one is your dynamic model. From this term you might have got some idea that okay, this is something which is once again a subset of the generalized model, right? This particular dynamic model provides information about quality over time, or maybe over the development phase. Like for example, like a general profile of defect distribution over different development phases can be considered a quality model of this type. So maybe we'll talk about, let's say, failure rate of during the requirement analysis phase can be some percentage. We can have like failure rate of design during a particular phase. Then we can have let's say a failure rate of coding, which can be of some percentage, and then later on we can have a failure rate of testing, and ultimately post deployment we can have some failure rate of support as well. So it is like this particular dynamic model is telling you the failure rates or the defect distribution over the different development phases, right? So overall development phases we have for this particular thing, and for overall product development I have different failure rates for different failure phases, right? So what we have is in this case we have a very popular model, which is your Putnam model, right? So it was given in the 1978, which is like a very well known model, so which generalizes the empirical effort and the defect, and this basically comes up with a curve. So this profiles over time into a Rayleigh curve, right? Rayleigh curve, I guess everyone is aware of. If you're not sure, so maybe we can throw some light on. Rayleigh curve as well. So in this case, like fine-grained dynamic models may measure the precise time instead of the rough time corresponding to the development phases. The most well-known model, of course, is the Putnam, where it generalizes the empirical effort and the defect profile into a Rayleigh curve. Then what we have is, in case of your Putnam model, this is like a very traditional one. As you can see the date, it came in the year 1978. So this is basically the Putnam model, which is coming up with this empirical software effort estimation, right? So when we talk about empirical, so this is based on the kind of observation we do, right? So that means we went for the empirical evidences, right? So, and it is like the original paper was given by Lawrence H. Putnam in the year 1978. It is like one of the pioneer work in the field of software process modeling. And what we do is, like, here we collect the software project data. It can be in the form of your efforts, it can be in the form of size, like effort in case of function point analysis, size in case of your LOCs or KLOCs, and then we fit a curve to the data. So as, like, further the future effort estimates are made by providing the size and calculating the associated effort using the equation which fit the original data. Right, recall our previous discussion of performance estimation, where there also we were doing some amount of curve fitting as well. We were talking about least square approximation in order to minimize the errors. We were using some previous data and we were coming up with some estimates, right? We were coming up with some estimates. Similarly, in this particular model also, we are using some past data and then we are coming up with some estimates, and we are going ahead with some curves. Here what we get is, we get the estimates of the process and the productivity as well, right? So Putnam basically advocates obtaining the process productivity by calibration, right? So this can be in the form of your process and your productivity, and it makes a sharp distinction between your conventional productivity and your process productivity, right? So it's like what we say is like, so estimation, basically we are talking about the estimation. So estimation in software engineering, we have already talked about, is basically concerned with the effort to develop and test the software. So we make the prior estimate of everything, right, from the efforts to the budget to the size to the problems and so on and so forth, right? There we can have like analysis effort methods, we can go ahead with parametric estimations and so on and so forth. So it's like we can reach into a totally different kind of study where we can talk about your estimation theory, right? So basically we can once again talk about your statistics, right? So we can estimate the parameters based on some of the measured empirical data from the past projects. So that kind of thing we can do. In case of function point analysis, we are doing the same. In case of response time prediction, we were doing the same. So in both the categories, we were talking about the estimation and prediction. So here also it's like your Putnam model, which is talking about the same one. I guess your Rayleigh curve, everyone is familiar with your Rayleigh curve. This thing, you might have studied this particular topic in one or the other places, right? So when we talk about Rayleigh curve, so it, as I said, it has been used in your Putnam model. So in the study of your software project scheduling, we use your Pnr curve, which is your Putnam Norton Rayleigh curve. And what we do is, in this particular thing, this is basically an equation specifying the relationship between your applied effort and the delivery time of a software project. So a Pnr curve is used to determine the least cost time for delivering up to a particular limit. So it can be your full project delivery or it can be your partial project delivery with some modules working. And the absolute minimal amount of time required to complete the project, and irrespective of how many people we are adding to it. So that for that particular estimate we use this Pnr curve, which is your Putnam Model Rayleigh curve. Right. So next we'll talk about your product specific quality evaluation model. So that will there we'll see the semi customized model, we'll see observation based model, we'll see measure driven predictive model in the next video. See you soon.